Hi, I'm Zor. Welcome to Unizor Education. So we will continue talking about Lagrangian, about Euler-Lagrange equations, about generalized coordinates. And what's important, we are going to introduce another reason why generalized coordinates in many cases are significantly better than using Cartesian coordinates and Newton's second law. So, generalized coordinates with Euler-Lagrange equation is subject of this particular lecture, and one particular case when it's really very, very important I'm about to present. So the case is related to constraints. So my point is that if you have some kind of a movement of mechanical system which is constrained by certain constraints, then it's much better to use generalized coordinates in Euler-Lagrange equation. This is just another reason for introducing all this thing. Okay, so this lecture is part of the course called Physics Plus for All. It's presented on unizor.com. I suggested to use to watch this lecture from the website because it has a textual part, notes, which is like a textbook. And the website is totally free. There are no advertisement. You can just use it the way you want. And there are some prerequisite courses, obviously. There is a math for teens. There is a physics for teens. There is a math plus. And this is part of the physics plus. Okay. So let's get to this particular case. So we know that in Cartesian coordinates, Newton's second law is equivalent to Euler-Lagrange equation. They have exactly the same solutions. Mechanical system, movement of mechanical system will be derived in exactly the same fashion as functions of time in both approaches. Now, also, Euler-Lagrange equations are good in generalized coordinates, which is not the case with Newtonian's approach, because forces and accelerations, they're all really vectors, and vectors are very nicely falling into the Cartesian coordinates universe. Whenever you're talking about like angles, what is the vector if coordinates is angle? Well, again, you will probably have to introduce some local Cartesian coordinates to describe this vector with 3 projections or n projections, whatever. So now I'm going to present a case when the Newtonian approach in Cartesian coordinates is really so much more complicated than using generalized approach and Euler-Lagrange equation, that you will immediately agree with me that in case of constraints, it's definitely much better to use generalized coordinates and Lagrangian. Okay, here is a very simple example. We have basically did it a couple of times already. So you have a pendulum. This is a rigid rod. This is weightless, obviously. This is some kind of a bob which goes along the circular trajectory. Now, let's do it in a purely Cartesian coordinates, Newton's second law, etc. So, what is Newton's second law? Well, the second derivative, mass times second derivative of x, is supposed to be projection of all forces on the x-axis, and mass times second derivative of y is supposed to be equal to sum of all forces projected on y-axis. All right, great. So this is my x-axis, this is my y-axis. Going down, it's easier because it's a mg, and this is some kind of a tension force T, and the length of the rod is L, let's say. So we have 2 forces. Well, if this angle is theta, then now this point is xy. So what's the projection of T onto x-axis? This part. Now, if t is unknown magnitude of this vector, then the projection on the x-axis would be, well, first of all, it goes this way, so it's minus t times, now this is theta, so this is theta, sine of theta. What's sine of theta? Sine of theta is x divided by L. Now ty is equal to minus t, it goes up, that's why it's minus, y divided by L. Alright, now the weight x is equal to 0 because it's vertically down, so projection on x is 0, and weight on y is equal to mg. There's a plus because it goes along this. So now we have very simple equations. Mx double derivative by time is equal to minus tx over L. L is a constant. And mass y double derivative of time, which is acceleration, is equal to sum of these, which is mg minus ty divided by L. Well, we have three unknown variables, x, y, and t, but we do have a third constraint. This is a constraint. This is what we talk about. This is what this lecture is about. So this is extra equation which gives us the ability to get rid of t and to reduce this system. Well, basically all I'm saying is the system is ready. There are three different variables and three different equations, 1, 2, and 3. That's it, right? Well, but let's just try to, approach some kind of a solution to this. And it's a solution which is actually complex. Well, it's relatively complex already because we have a system of three different equations. If you remember, we never had anything like system of three equations whenever we were doing it in a regular way using the theta, which is not a Cartesian coordinate. Angle is not a Cartesian coordinate. We were using theta as main variable from which we derived all the movement of the bob. But now if you want to do it in Cartesian coordinates in a regular Newtonian system, that would be a problem because we already have three equations with three variables rather than one equation with only one variable, which is an angle theta. Alright, so let's try to solve it somehow. Well, I read this particular approach in one of the books some time ago. You see, we have to use this thing somehow creatively. So what's the creative thing is? We will multiply this by x and this by y and add them together, so it will be x squared plus y squared, so we will get rid of this, replace it with L. So what will be? So this by x would be mxx double prime is equal to minus t x squared divided by L. We multiply by x, right? Multiply by y this one, but let's just transfer this mg to the left equal sign. So it would be my double minus mgy is equal to minus t y squared by L. So we multiply this by x, this by y, and now we will add them together. And that would allow us to, this is minus t x squared plus y squared, which is L squared divided by TL. And this would be m times x double plus y double minus gy. Okay, now we can get rid of t. T is equal to this divided by minus L, so it's minus m divided by L times x double plus y double minus gy. Okay, now what should we do? Well, we put this and substitute in these two equations, and we get rid of t, right? So what is it? mx double is equal to minus, instead of t, I will put this one. So it would be m minus t, and minus would be just m over l times x over, so it's x l square, and x double plus y double minus gy. Am I right? I think I'm right. And we can get rid of m. Now y would be equal to y mg minus t, so it's mg minus something like this, yl square x double plus y double minus gy. And also we can get rid of that. Now we have two variables, x and y, with two unknown, with two equations, differential equations. It's still difficult. I mean, look at this: x times x double prime, which is basically the second derivative. It doesn't look actually good, and I would like actually to separate the first derivative, the second derivative, or free member somehow. Maybe I can simplify it a little bit further. Yes, I can. Just as an approach, what I can suggest is the following. I don't like this particular equation, this particular expression. I would like to simplify it somehow. Well, I can do it. If you will differentiate this by time, you will have what? 2x prime plus 2y prime equals to 0. L is a constant. And again differentiated by time. Well, get rid of 2 because it's 0. Differentiated by time, it would be x double plus x1 square, right? If you will, this is product. This times derivative of this plus derivative of this times this. So that's what it is. And this one as well. And that's equal to 0. From which I can derive x double plus y double is equal to minus x prime square plus y square. It's kind of separated between different degrees of, so we will have x double is equal to x over l square, and that we will have, instead of this, I will put minus y square, where is it? Yeah, minus this plus this, x square plus y square minus gy with a minus. So minus this, and y double is equal to, again, y over y square times minus x square minus y square minus gy. I don't know if it's L square, sorry. I don't know, it might be a little simpler, but in any case, it's solvable, but not in algebraic functions. It's solvable with the elliptical integrals and stuff like this. I'm not going to continue this because it's really kind of complicated, and nobody needs it right now. Why? Because there is a better approach. My purpose to do this was just to demonstrate how difficult it is to deal with constraints in Cartesian coordinates and Lagrange and Newtonian second law, even in such a relatively simple case. So scratch this. Now, how did we do it before? Well, before we have introduced an angle theta and then we want to use Euler-Lagrange equation, which means we want to use the Lagrangian difference between kinetic and potential energy. How to do this? Well, very simply. Now, what is kinetic energy? Kinetic energy is 1/2 mass times linear speed square. Now, what is linear speed if the body is going this way? Well, it depends on an angle. If angle is theta of time, the angular speed is theta prime. That's an angular speed. And the linear speed is L times square. Linear speed is L square. But whenever we are substituting to this, we will have 1/2 m L prime square. That's it. Now, potential energy. Well, let's say this particular top is relative to the ground at height h. Well, then we have to subtract this piece, which is L times cosine. So it's mass h minus L times cosine theta. Now, the difference between them, relatively simple thing. And now we basically do Lagrangian is equal to 1/2 m L square theta prime square minus m times h minus L cosine theta. So that's Lagrangian. Now we have to construct dl by d theta is equal to d time of dl by d theta star, which is very easy to do. This one is basically depends only on this guy, right? This is a constant, so it's minus and minus, so it's plus. So it's basically derivative by cosine, which is so in this case we can consider L to be equal only m times L times cosine, and we differentiate it by, it would be ml times derivative of cosine, which is minus sine theta, times derivative, no, that's it, partial derivative, not by time, that's it. Now, and derivative of this by theta prime would be 2 and 2 would be ml squared theta prime, and then by time it would be ml squared theta double prime, from which follows what? Cancels out. Here is an equation. Simple. Okay? So, that was my demonstration of why we should use really a generalized coordinate, in this case, one single coordinate theta, instead of two Cartesian plus constraints, because using this already implies that we are using the constraints. This length is fixed. Because it's fixed, I can use this type of things, this type of equations. So this particular approach, which is a smart approach, I mean, I'm not using any kind of coordinate, I'm using some really coordinate which allows me to do it simpler. In this case, it's angle. So if you know your restrictions, your constraints, you can rightly choose coordinates in such a way that it will completely bypass all these logic about constraints. That's what it is. Now, let me try to generalize whatever I was talking about in this particular case. Consider you have a space, let's say three-dimensional space, and one particular point is moving, point mass is moving in the space. And let's consider that there is a constraint. Well, there is one constraint. Let's say it's x squared plus y squared plus z squared is equal to r squared. So we are talking about Cartesian coordinates x, y, and z, and we are talking about concrete constraints in this particular case, and this constraint means that the movement of this particular point mass is supposed to be only geometrically where? On the surface of this square, of this sphere. So this is an equation of a sphere in three-dimensional case, and if this is a constraint, it means that the point is supposed to be on the surface of this sphere. Now, if under normal non-constrained conditions, position of the point is defined by three parameters, x, y, and z, how can I define position of the point if I know that it's on the surface of a screen? Well, simple. You have parallels and meridians, so you can latitude and longitude. You can use these two parameters, two, not three, two parameters, longitude and latitude, to position a point on a sphere. Okay? So instead of three parameters, you have two. So initially you have three-dimensional world. You have one constraint, and as a result, you can describe the movement on sphere, constrained by a sphere movement, by two parameters. Here is what I have written. Now, let me generalize. If I have a movement of a system in n-dimensional configuration space, S1, etc., Sn are coordinates. Maybe it's a Euclidean space with a Cartesian coordinates, doesn't really matter what it is. Now, let me introduce one particular constraint. Let's say f of S1 Sn is equal to 0. Now, what does it represent geometrically? Well, it's a surface. And what's the dimension of this surface? Well, it's one dimension less. Like sphere is a two-dimensional. One constraint gives you a surface of a sphere. Now, if you have another constraint, let's say something like x plus y plus z is equal to 1, something like this. What is this? It's a plane. Plane also is two-dimensional world. I mean, there are two parameters which can be defined, which we can define to determine position of the. So in any case, any kind of a equation like this defines one less dimension of a surface. So instead of n-dimensional space, we have some kind of a surface, and on this surface, we can use n-1 parameters. So the degrees of freedom, so to speak, in this particular case is 2. In this particular case is n-1. Okay, great. What if you have 2? Let's say this is 1, and this is another constraint. Well, this is also a surface of dimension n minus 1. But now if we are talking about two of them, we have to intersect two surfaces. If you intersect, let's say, a sphere and a plane, what do we have? Some kind of a curve, right? A circle, actually. Okay, now that's one-dimensional thing, because if you are on a curve, then the position can be defined by only one parameter, the length of some beginning. Then you just go along this curve and you have one parameter. So every additional constraint reduces again by one. And if you have m constraints, they reduce it by m. Okay, there is only one little condition which I have to talk about. These are not just any equations. I mean, we have to really be more specific about this. For instance, if this equation is derived from this by multiplying by 2, it does not add anything, it does not intersect, it basically coincides. So we have to put some kind of conditions on these constraints if we would like to use the formula like this. So my n-dimensional world with m constraints produces a mechanical system with n minus m degrees of freedom, or parameters which are sufficient to define position of the system, in kind of, special cases, but it's generally rather broad cases. So first is independency. Dependent. They're not supposed to be derived from one another. Okay, I can actually define it slightly more mathematically, so to speak. You know what gradient is, right? So if you have a surface, some kind of a surface, then gradient is a perpendicular to every point. And it can be defined with partial derivatives, etc. So what I'm saying is that any two systems should not have the same gradient at the same points, basically. So at the same S1, Sn. So that's what actually means that they are not derived from one to another. So all these gradients must be completely linearly independent, so to speak. Because if gradients of, I mean, maybe one function is the sum of two other functions, so that's what makes it linearly dependent. So what I'm saying is that vectors of gradients of all these surfaces should not be linearly dependent from each other. So that's one very important case. And then another thing is holonomic. They're supposed to be only functions of positions and optionally of time. No dependency on, let's say, speed of derivatives of s by time. So if it's just positions and time, then this is called holonomic. So these are supposed to be holonomic constraints and independent from each other, or if you wish, their gradients are not supposed to be linearly dependent, more mathematical formulation. Okay, these are conditions under which this particular theorem is true. If you have n-dimensional configuration space where our mechanical system is moving, these are coordinates, doesn't matter which ones. And you have m constraints which are independent and holonomic. Then the result is that our system is moving in some kind of a intersection of all these surfaces, which is a movement of n minus m degrees of freedom, which means there are n minus m parameters which we can devise. We can kind of smartly choose these parameters, And we don't really need, after this, we don't really need to know that our system has all these constraints. We don't need to use S1, Sn. We will use something like Q1, etc., Qn minus m to define position on this particular surface, which is the result of intersection of many of these surfaces. And then our system would be significantly less, n minus m equations with n minus m independent parameters, instead of, as if we are using Cartesian system with constraints, it would be n equations for each coordinate using Newtonian second law, plus m equations of constraints, and that would be n plus 1, n plus m equations. So instead of this number of equations and variables, we use this number of equations and variables. And the more constraints we have, the more dramatic the difference will be. Okay, thank you very much. That's it. You probably should read notes on Physics Plus in this particular website. You go from Physics Plus, you go to Lagrangian chapter, and this is the lecture called Constraints. That's it. Thank you very much, and good luck.